for the invitation to speak. And thanks all for coming. Yes, I will talk about low-lying zeros, and most of what I'll tell you, at least eventually, will be joint work with Martin Čech, Lucile Devin, Daniel Fiorilli, and Kaisa Matomäki. But I'll start with some introduction, and let's see if I can switch slides. Zeros of L functions, that is generally a rather tricky business. So somehow understanding zeros is a well-known hard problem. So somehow trying to understand statistical properties of zeros is a natural thing to be interested in. And investigations in that direction has pointed to this connection between zeros of L functions and eigenvalues of random matrices that first appeared in the work of Montgomery on the pair correlation of zeros of the Riemann zeta function. So I thought I should start there. So somehow this pair correlation of Riemann zeros. So if n of t is the counting function for the zeros up to height t of the zeta function, we know from the Riemann von Mangold formula that there are roughly t log t over 2 pi such zeros. So the average spacing is about 1 over log t. And if we try to study the number of pairs of zeros whose distance is somehow on the measured on the scale of the average distance, then you get the pair correlation function. And what Montgomery found was that this is related to a corresponding quantity related to random matrices or random Hermitian matrices. And I have a picture of my cup here because this is somehow the famous T discussion in Princeton between Montgomery and Dyson that led to this discovery that zeros of the Riemann zeta function and random matrices are connected. So after this was somehow verified numerically to remarkable precision by Otlysko in the 80s. And after that, somehow, I think Hedgel went to triple correlations. And then after that, Rudnick and Sarnak proved that higher level correlations, not only for the zeta function, but for more general automorphic L functions, agree with random matrix statistics, at least for certain limited test functions. So that is history, and somehow after that, it seems like if you take a single L function, you always get the same sort of random matrix statistics. It was realized that if you only look at zeros very close to the real line, then there is a slightly different but similar story. So that is the Katz-Sarnak heuristic. So focusing on low-lying zeros, that is zeros that are suitably close to the real axis, and not in a single L function, but in a family of L functions, then if there's a family is not too pathological, so in a reasonable family of L functions, the statistics for low-lying zeros should resemble statistics of eigenvalues that are low-lying in the sense that they are close to 1. In one of not only one group, but in 5 possible compact Lie groups of matrices. And there should be a scaling limit as n tends to infinity, and eigenvalues should be normalized correctly. So there are now 5 possibilities, and these are the sort of the random matrix models are called symmetry types, and either unitary, orthogonal, special orthogonal with even side of the matrix, or special orthogonal with odd size, or unitary symplectic. So returning to low-lying zeros. So yes, they are close to the real axis, but how do you measure that? So first, if you take an L function, we write I will write the zeros as 1/2 plus I gamma j of L. L is the L function. So the jth zero is this one. I do not assume the Riemann hypothesis, so this gamma L could be complex with a small imaginary part. So how do we then measure or study low-lying zeros? Well, low-lying zeros, they should be close to the real axis. And there are certain functionals. For example, the one-level density that is depicted here, that depends on the family, a test function, and some parameter that says, okay, take the test function and evaluate at what we can think of as the imaginary part of a non-trivial zero of the L function, normalized by 2 pi, and then some number that should be suitable to somehow just pick up the first few zeros of the L function. And then there is an average over the family, or at least over some finite part of the family, and x should be a parameter that somehow exhausts. So f of x exhausts the full family as x tends to infinity. So there's a family average, and inside there's a sum over zeros, but this constant here should be chosen so that there are essentially only a few first zeros that are counted from each L function. So how do we pick this C of L? Well, a natural choice is take the logarithm of the conductor of L, or some approximation. So this is a rather robust statistics. So if you change CL a little bit, typically it doesn't change the statistics much, at least not when it comes to main terms. So somehow there are several choices, and in various problems it can be somehow good to change a little bit, not take exactly this log of the conductor of the L function for computational reasons. Okay, so this is statistics, and how do we work with this? Well, so a sort of general strategy is to look at the inner sum, the sum over zeros. Since zeros are hard to understand, at least typically, the explicit formula is an important tool, and that changes the sum over zeros. There are some terms that I removed here because they are easier to understand. The upshot is that it replaces the sum over zeros with a sum over primes or prime powers. And that is typically somewhat easier to understand. So it's easier to work with the right-hand side rather than the left-hand side. So here is the Dirichlet coefficient of the logarithmic derivative of the L function, and this is the Fourier transform of the function phi on this side. So one switches zeros to primes or prime powers, and then the next step is typically to interchange the orders of summation upstairs, so that instead of having the family average outside, it's moved inside, and then one averages, for example, these coefficients, and okay, depending a little bit on how this varies, but that turns into essentially to an average of coefficients of the logarithmic derivative. In this step, there's often some things to be gained from assuming a relevant Riemann hypothesis, but not always. Okay, so returning to the Katz-Sarnak heuristic, there is the so-called density conjecture. If we zoom into zoom in on the one-level density, the conjecture is that, well, if we look at, this is a statistics for low-lying zeros, it should be modeled on what happens for random matrices. And here is the sort of corresponding statistic, limited density for rescaled eigenvalues close to 1 in the symmetry type random matrix model for the family. So this should happen as x tends to infinity. The one-level density for the L function should tend, for the family of L functions, should tend to a random matrix analog. And this is nice because somehow the right-hand sides for all the 5 symmetry types, this is explicit. So for example, today the orthogonal type will be important, and then the density in the above integral is this one. So this is the Dirac delta at 0. And for example, I also wrote the unitary symplectic, also explicitly known. But somehow the disadvantage is that we have to calculate this left-hand side, see what we get in the limit, and then compare to the 5 known right-hand sides. At least it used to be like that, but more recently, work of Sarnak, Templier suggests that at least for what is called parametric families of L functions, one should be able to just calculate 3 numbers, 3 indicators, and that should tell us which symmetry type to expect. I don't write more than this because one also have to somehow determine a Sato-Tate measure for the family and so on. So there's a lot of things going on here, but in principle, there should be a way to not calculate the left-hand side and still know what to expect in the right-hand side. Just to have one example before we set out, explicit example for a family. One family that I think many have seen is the family of quadratic Dirichlet L functions. So L is chi-D, where chi-D is the Kronecker symbol, and D is a fundamental discriminant. So this is was perhaps the first family to be studied in this sense. And the density conjecture is that this family has symplectic symmetry type, so USP infinity. And there are a lot of partial results. Snyder studied the one-level density, and as soon as the support of the test functions Fourier transform is bounded by 2, the density conjecture can be proved, but that is a typical restriction, that one has to make some sort of restrictions on the test functions to get actual theorems. And there are many others that have contributed to partial results towards this, and I think that this picture is borrowed from Rubinstein and his early numerical work on these zeros. And somehow in this family, it's easy to point also to an application. So the question of zeros are interesting in their own right, but somehow there is often what happens at the central point is particularly interesting. And this old conjecture of Chawla says that for primitive quadratic Dirichlet L functions, they should not vanish at the central point. And the best known unconditional results are for this subfamily of quadratic characters. Sound proved that 87.5% of them are non-zero. But from a result on the one-level density, as Snyder showed that, okay, it's conditional on the GRH, but still, assuming GRH, 93.75%, or so 15 by 16 of the percent of the L functions are non-vanishing. So there is somehow a lot of interest and also applications towards questions like this. Okay, so that was the introduction, and now I want to move towards the work that we have done with Čech, Devin, Fiorilli and Matomäki, where we consider L functions attached to holomorphic modular forms. And let me say something about the setup. So I'll let k be even and n square-free positive integer. And then somehow be interested in Hecke eigenforms. So this is a basis of Hecke eigenforms, bk star n, where k is the weight, n is the level, and we are considering the space of new forms. So forms which do not arise from lower levels. And in this situation, each form can be written as or it has a Fourier expansion. And we will normalize the Fourier expansion so that the first coefficient is always 1. And in that situation, the Fourier coefficient here will be the Hecke eigenvalue for the nth Hecke operator. And moreover, for such forms, the L function, the associated L function is given explicitly with the same coefficients lambda f of n times n to the minus s. So here, as the real part of s is assumed to be greater than 1, so that we have this usually series representation, and there's also an explicit Euler product. In this case, what does the one-level density look like? Well, we will work with something which looks slightly different from what I wrote before. So I'll try to say something about this. So here is the normalization. It was called CL in my earlier slide. So in this case, all of the functions in this family will have the same analytic conductor, which is k squared n. But somehow for convenience, it will be called x several times in this talk. But perhaps more interesting is this number. So instead of having a sharp count, there are some weights in this one-level density. And the weights are put there to somehow for convenience, computational convenience, so that it's easier to apply directly the Peterson formula in a later stage. And then outside here, do not divide by the size of the family, but the total weights, so the sum of all weights. So capital omega k is the sum of all the weights. So how serious is this? Well, so these are in some very vague sense approximately constant, or at least of roughly the same size. So in some sense, it's not brutal, but somehow it is some weight that we put here. Again, there is a test function, a Schwartz function. It will assume to be even. Fourier transform should have compact support. But otherwise, I think it's mostly as before. The weights, they are written explicitly down here in terms of the Peterson norm and the gamma function. But I think that this expression is perhaps not very illuminating, but that is what it is. Okay, so this is the object we want to understand. We would like to study this functional. And the sort of first results and also some of the landmark results in this direction are results of Ivanits, Lu, and Sarnak. They wrote a paper that is long and contains an awful lot of nice results. And what I'll present is just a very small part of what they did. But in the special case where k, so that is the weight of the modular form, is fixed, and n is allowed to grow towards infinity. If we suppose that the test function phi is so that the support of its Fourier transform is bounded in this sense, so it lies between -1.5 and 1.5, then the density conjecture in that for such restricted test functions holds. So here is the random matrix integral for orthogonal symmetry. So this is what we get unconditionally. Moreover, if you also assume the relevant Riemann hypothesis, so that means the Riemann hypothesis for the modular L functions, but also for Dirichlet L functions, then this result can be extended so that the support, the Fourier transform of the test function is in the larger interval from -2 to 2. So this is one option. One can let k be fixed and let n run to infinity, but one can also do the opposite and see what happens when one fixes n and let k tend to infinity. And there's results also for that in Lucile-Devin's paper. Then the restriction is stricter on the support of the Fourier transform. Apart from that, there is a density theorem of the same type as up here, so I didn't write it again. So here it's interesting that even if one assumes the Riemann hypothesis, this is not improved. At least not if not other things are assumed. For example, if one take an average over weight in some range, so instead of letting k tend to infinity, take k in some dyadic range, for example, and let that range tend to infinity, then one can double the support and get the same result as up here. But that is somehow a slightly different story. As I said, they prove many other things. And one of the things they prove is that one can combine these things and let k and n tend to infinity at the same time, but that will not be somehow of interest in this talk. What will be of interest is somehow this first theorem, and the fact that there's some unconditional bit, and then assuming Riemann, one can improve that result or extend the result. So one can say that one can ask the question, okay, can we do, there is some room between 1.5 and 2, and can we extend the unconditional part of this theorem? That was, at least to a large extent, a motivating question for the work that I'll present. And somehow, yeah, I'll just squeeze back to the previous page that here, not even assuming Riemann helps extending the support. So somehow that seems very hard to do something unconditionally. And that is at least part of why we restrict this first case, where k is fixed, and the level n runs to infinity. As far as I know, the history is that the next improvement to the result of Lucile is by Ricotta and Rougier. And they improved the unconditional result from -3/2 to 3/2 to this number. And this depends on the weight k. So as k grows, we see that this becomes closer and closer to, or rather this becomes closer and closer to 2. Somehow it becomes better and better in the sense that getting closer and closer to the conditional result on the ERH. And also Ricotta and Rougier, they proved a lot of things, and this is just one tiny bit of what they did. They did higher symmetric powers, but somehow they also got this improvement on the Devin-Lucile theorem by handling Bessel functions in a slightly different way. So this is a restatement of the previous theorem. So a couple of years ago, Lucile Devin, Daniel Fiorilli, and myself got interested in these results, and we managed to improve further somehow this support condition from Ricotta and Rocher to another support condition. So here the support is from minus theta k prime to theta k prime, and theta k prime is such a number where k equals 2 is slightly special. It is this number, and if you don't see it immediately, this is roughly 1.866. So comparing to 1.5 from Ivanitslu-Sarnak, and for k equals 2, this is also 1.5. That is a rather big improvement. But then somehow for larger k, this is of the same rough shape as the Ricotta-Rocher result, but somehow instead of 1 over k, this is roughly 1 over 5k. So it goes to, this approach is too slightly faster. This happened a couple of years ago, and the new result for today is joint with Martin Čech, Lucile Devin, Daniel Fiorilli, and Kaisa Matomäki. And this says with more words what I've said in the previous theorem. So we fix the weight, take a test function phi. The support of its Fourier transform is in some range, and this is now a slightly cleaner expression that is the same for all k. And for this new number, as n tends to infinity, through prime numbers, we have a density theorem in the Katz-Sarnak style. Again, the symmetry type is orthogonal. I didn't say it, so let me return to the previous slide. In all these cases that improve of Ivanitslu-Sarnak in the support condition, there's one price. There's the price we pay, and the price is paid by not having square free and running through square free numbers, but now just prime numbers. Same in this theorem and the same in the new theorem, and run through prime numbers towards infinity. Then we get a density theorem. So I rushed through various previous results. So here is everything in one slide. So ILS is Ivanitslu-Sarnak. This is Ricotta-Rocher, Devin, Fiorilli, and myself. Čech, Devin, Fiorilli, Matomäki, myself. So we can see that one should really read it one line at a time and see that the improvements are the largest for k equals to 2, where the history was 1.5, 1.5, and then 1.866. And with the new theorem, it's getting closer to 2, but still there's quite some gap. So 1.875 is the new support condition. For k equals to 4, there's a big gap from 1.5 to 1.75 of Ricotta-Rocher. And from that, rather big gap, then a smaller gap. And somehow the gaps are getting smaller. And one can see that somehow that here, yes, the gaps are getting smaller. And in the last step, it's asymptotically, the difference is just 1 by k squared. So somehow getting really tiny when k is growing. So it's so most significant improvements, they happen for low weights. Okay. So I will hopefully have time to say something more careful about the proofs in a little bit, but let me say something just quickly about the proofs. But all these results, they start in the same way by using an explicit formula that replaces sums over series by sums over primes, and then uses a Peterson trace formula to make some averages of Hecke eigenvalues, and that produces Klosterman sums, or rather sums of Klosterman sums weighted by some Bessel functions. And then one can use the wave bound for Klosterman sums and bounds for Bessel functions and attack them directly, or as in the 2022 result with Daniel and Lucile, what was new there was an idea that we rewrote Klosterman sums in terms of Dirichlet characters. And then with that expression, one could do Mellon inversion and then massage that a little bit to be able to apply the explicit formula again, but now in the other direction. So instead of having prime sums, we went to sums over zeros again. So somehow we went from zeros to primes, and then eventually from primes to zeros, but not for the same L functions. We start with modular L functions, and now it's Dirichlet L functions. And the upshot is that somehow we know more about the Dirichlet L functions, and then we could use zero density estimates for those to get the new result. And with the new theorem, the five-author theorem, the idea is similar, to start somehow by using Dirichlet characters and orthogonality to rewrite Klosterman sums. But then instead of using zero density estimates, we use the Heath-Brown identity for the von Mangold function, and then bounds on Dirichlet polynomials to obtain the result. And this is slightly interesting because in some cases, these two approaches, using zero density estimates or bounds on Dirichlet polynomials, give results of give the same results. So, for example, for primes in short intervals, using zero density estimates or this sort of machinery, that gives the same result, because somehow the bottleneck cases here turn up as bottleneck cases also for such methods. But for the problem that we care about today, this is not the case, and that is it just turns out that the bottleneck case in this work transforms to or corresponds to something which is not a difficult case in this new technique. So one can push a little bit further. But that seems to be, in some sense, luck, and I don't understand fully exactly why it happens, more than I can see that it happens and somehow, but I don't have a good explanation for. One can hope that this should work for some other families. So another remark on the proofs is somehow that key to both these methods is that we have this relation between modular form L functions and Dirichlet L functions. And the relation in itself is not new. So already in the work of Katz-Sarnak, they use this in many ways. So the new, it's rather how we use the connection, and that for example, when we use zero density estimate, when we circle back and get from characters to zeros of Dirichlet L functions, that is somehow a new component. Also using zero density estimates is not new. That has happened in many other families. But the new thing in this case is that, let me see if I can go back. So here, when we start with modular form L functions, the typical thing previously has been that then one use zero density estimate for such L functions. But here we start with modular form L functions, and then in the end we use zero density estimates for another family, and that is, as far as I understand, a novel aspect of this. And the final comment here is just that somehow this connection between modular and Dirichlet L functions also appear in other works, for example, on cubic moments, where there has been recent work, for example, of Petrov-Young. Okay. So I've spent some time now talking about the situation for holomorphic modular forms, and there is a parallel story for Maass form L functions. So I will at least briefly say something about this case. It's slightly more notation to set it up, but it's similar that we have n, a prime number, which is the level in the family, and then we look at an orthogonal basis in a space of forms. Now it's Maass new forms on that level, and somehow we make simultaneous diagonalization so that these are eigenfunctions of the Hecke operators, or rather the hyperbolic Laplacian, all Hecke operators, and this sort of reflection operator, reflection in the imaginary axis. And write the sort of Laplace eigenvalue as a quarter plus Tf squared, so f is the form. Lambda f is again the Hecke eigenvalue, and this is the even or odd symmetry around the imaginary axis. Very similar to before, these functions have Fourier series expansion, and they look slightly more complicated because now there are k-Bessel functions involved. But we normalize again so that all these have rho f of 1, the first coefficient is 1. And then these rho f's, okay, I see that there is a mismatch on the slide, sorry. Then in this situation, the rho f is equal to the Hecke eigenvalue lambda f, and that is what appears in the L function, which looks exactly as before. Again, there is a weighted one-level density. So the inner sum is what it used to be, or at least very similar. So there is a, these are, you can think of this as imaginary part of the zeros. This is an approximation of the log of the analytic conductor divided by 2 pi. But now there are two weights outside, and this omega star, well, is the total weight again, but with these two weights. So in parallel to the holomorphic case, there is a spectral weight that is coming from, normalization in the problem, say. And then there's an extra weight here that we put that should work well with, instead of the Peterson formula, now we would like to use the Kuznetsov trace formula, and then one needs some sort of a suitable weight in order to apply that. But apart from that, there is a similar weighted density here, and the expectation, Katz-Sarnak prediction, or density conjecture, is that this should also be orthogonal, this family. And there is work by Apog, Amersi, Iger, Lazarev, Miller, and Zhang that has the same condition as Ivanis Lucile had for modular form L functions. So -3/2 to 3/2. And if n tends to infinity through the square free numbers, they have a density theorem. And also in this case, it's true that if one assumes the Riemann hypothesis, one can improve this to -2, 2. And then the question is, what can we do unconditionally in this case? And our method worked equally well in this setting. So here we have, again, an even Schwartz function, support condition, which is now from -15/8 to 15/8. This should be compared to on the previous slide. The result was -3/2 and 3/2. So this is 1.875. And with that number, if we keep the Kuznetsov weight function fixed and let n run through prime numbers to infinity, then we have a density theorem. So here there were only two results, so I will not make a table, but one can still think about this 15/8. How does that compare to the numbers we saw in the for holomorphic modular forms? And 15/8 is, as I said, 1.875. And that was the result we got for holomorphic forms of weight 2. So somehow this situation can be compared to holomorphic forms of weight 2 then. Sorry. Then we have results of a similar magnitude. Okay, so these are the results that I wanted to present. So one for modular forms and one for Maass forms. And for the remaining minutes, I would like to say something about more detailed about the proofs. Okay, so I now restrict to the holomorphic case, mainly because then we don't have the extra weight to keep track of. So this is the one-level density that we would like to understand. And as in the general philosophy, we start by replacing the sum over zeros by sum over prime powers via the explicit formula, and then interchange order of summation, and then one can use the Peterson trace formula, which is so formula that handles expressions like like this. So we get Bessel functions and Klosterman sums. And one immediately, or more or less immediately, get the Katz-Sarnak main term, and some expressions that one can bound immediately. But there are some parts which we cannot treat immediately, and that somehow remains to be bounded. So just excuse me for a second. So you would like to understand the sum. So I copy it again, and somehow SP nu, 1, C is the standard Klosterman sum. And the Bessel function can be bounded, at least for small x, very efficiently. So the trick is to move to, or introduce characters, and we do that by orthogonality. So like, place the Klosterman sum by an average, like this. And if we then want like to interchange order of summation, you see that sums of this shape will appear. And this is just a Gauss sum squared. So here there are things that are really nice. So using that, and also truncating the C sum, and writing everything in terms of now primitive characters, we get something, a sum over C, and then of divisors of C. So these are now a sum over primitive characters. And then there's an inner sum that I wrote in red, which is what we really need to understand. And there are two approaches to this. which both more or less uses the Mellin inversion. So the sum in red, one can use Mellin inversion, where one take the Mellin transform of the phi hat times Bessel function. And then it turns into an integral of logarithmic derivative of the corresponding Dirichlet function times something. This is a rather large Mellin transform, but it turns out to be an entire function, and we can bound it rather well. So in the now slightly older result with Devin and Fiorilli, what we do is we use this Mellin inversion, and we shift the integral or the counter of the integral and pick up various contributions from the non-trivial zeros, something from that might happen at 0, and then the shifted integral. Here it turns out that these two contributions will be easy to handle, and what we have to do is we have to understand this, and this is where the now non-trivial zeros of the Dirichlet functions appear. So plugging this, this is the main term, so this main term sum here into this expression gives something, and dividing into subsums, we get some power of n times an expression where there are now inner functions. Well, this can be written like this, or a sum. This counts the number of zeros with large real part and bounded imaginary part. This is an expression exactly made to where we can apply zero density estimates. So somehow this is perfect in some sense. So that was the old result, and now in the more recent work with CDFMS, 5 authors, this was the sum that was in red before, and we start by using Heath-Brown's identity. So instead of writing the von Mangold function here, we replace it with an expression like this. We cut in dyadic ranges of these, so this is a multiple sum. And then we plug in the Mellin inversion. And doing all that, it turns out that in the situation we're in, Heath-Brown's method gives us a sum over 40 variables. And this is the size of somehow the dyadic range. So if you multiply them together, they should be bounded by something in terms of the support condition. And if we can then treat for suitable coefficients a, j, n, integrals of average over characters of this shape sufficiently well, then we are done. And how do we do that? Well, we have a combinatorial lemma that says, okay, these figures, 40 figures from the summation conditions, they come in two sets. Either they behave like there exists an index set such that the product of the corresponding nj is in between two numbers, or else there are two indices such that this product is bounded by something. And this gives at least one of them always holds. So we can somehow split into, when we do the integral on the previous page here, we can say, okay, we do this, but we do it in one of these two cases. And for example, in the first case, attacking the integral, then one can just divide into, okay, so there were certain indices that were collected in the index set I. We take them up separately, and the rest in the index set j separately, and we do Cauchy-Schwarz. We get an integral of this shape, and there one can just do a rather straightforward large sieve type bound. And this is enough to use in this second moment and in this second moment to get what we need. So this is rather direct. The remaining case, and I'll just spend one more minute on this, takes the integral we have and split it using Hölder into a second moment that we can treat as before, and then two fourth moments. So we need something to treat this fourth moment, or the two fourth moments that appear here. And we need something slightly more effective than the logictive second moment bound. And for general complex coefficients, we have expressions of this kind, and we can get, using the logictive second order bound or second moment bound, we get also in this case something. But we need something slightly better, and that is somehow with more work. And now I will not keep you for much longer, but somehow it includes as a crucial component a fourth moment bound for Dirichlet L functions. Then we can consider also coefficients which are not bounded. So, for example, logarithms that appear from the Heath-Brown identity, and then we can treat averages of this kind and get something which is acceptable. And putting everything together, we get exactly what we want. But I think that I've spent more than my time, so I'll stop here and thank you for your attention.